Hi everyone, in this video I want to teach you about a tool called polynomial long division. But before we learn polynomial long division, let's just remember how to do normal long division. It's been a long time since elementary school. So let's first just do this long division problem where we're taking the number 2015 and we're dividing it by 32. That's all that we're doing. So you'll remember that the way we set these problems up is we do 32 and then 2015. And we first ask ourselves, how many times does 32 go into 20? Well, it's bigger than 20, so it doesn't go in any times. Then we can ask ourselves, how many times does 32 go into 210 then? And it goes in 6 times. So I put a 6 up here. My next step is to do 6 times 32, and that is 192. And I write that underneath, 201. Now I subtract the 192 from 201. And what do I get? Well, these are different by 9. And then I bring down the 5. So now I ask myself I go through the same procedure. How many times does 32 go into 95? That's 2. Then I do 2 times 32, which is 64, and I'm going to subtract it from 95, and I get 31. So what does this whole process tell me? It says when I do 2015 divided by 32, this equals 62, remainder 31. It's important that the remainder is smaller than the thing we were dividing by, or else we could have fit more than 62 in there. So the remainder's got to be smaller. Another way that we could write this is that 2015 equals 32 times 62 plus 31. And if you don't believe me, you can just check it. 32 times 62 plus 31 is 2015. So that's exactly what we're saying here. It's like 2015 is almost 32 times 62, but we have to add in the remainder to get all the way up there. One other way that we could write this is that, say I take this expression, divide by 32. So then it says 2015 divided by 32 is the same as 62 plus 31 divided by 32. This is the most useful form, and we'll actually come back to this in just a minute. So that's our first example. We had a remainder there. What if we divide 2014 by 32? Then I go through the same process. We have 32 into 2014. Just like before, 32 goes into 201 6 times. We multiply 6 times 32 to get 192 and subtract it. We get 9, and then we bring down the 4. And if we have a 2 here, oh, this doesn't actually work. I wanted to come up with an example with no remainder. So let me see what that would be. 32 times 62. Okay, here we go. Let's divide 2016 by 32. So if I divide 2016 by 32, then same idea. 32 goes into 201 6 times. 6 times 32 is 192. Subtract it, and I get 9. Bring down the 6, I get 96. 32 goes into 96 3 times. 3 times 32 is 96. Subtract that, I get 0. So this says that 2016 is equal to 32 times 63 plus 0, no remainder. And what that tells us is that 32 divides evenly into 2016. So no remainder means 32 is a factor of 2016. It divides evenly into it. So now we want to apply all of these things to polynomials. So let's try an example, and I'm going to keep our example from before with numbers close at hand. So here we wrote 32 into 2015. Now I want to divide this big polynomial by another polynomial. So this is like the 2015, this is like the 32. The first thing I did here was I looked to see how many times does 32 go into the very first part of 2015. What I want to see here is how many times does x squared go into the first part. So what I put here is what times x squared equals x cubed. So what do I have to multiply x squared by to get x cubed? And the answer to that is x. So now I do the same process as before. I took the 6 and multiplied by 32. I'm going to take the x and multiply by this expression. So x times x squared is x cubed. X times negative 7x is negative 7x squared. X times 5 is 5x. So what I'm writing here is x times x squared minus 7x plus 5. Now in the regular long division I subtracted, so I'm going to subtract again. X cubed minus x cubed is 0, minus 5x squared minus 7x squared gives us, this is going to be 2x squared, because this will be a positive 7x squared. Minus 9x minus 5x is minus 14x. Now I do the process again. I look to see x squared, how many times does that go into 2x? That's just 2. So this is number of times x squared goes into 2x squared. So now I have to do 2 times this expression again. So I get 2x squared. Oh, and I carried this 10 down, just like I carried the 5 down before. So I do 2x squared minus 14x plus 10. This expression is 2 times x squared minus 7x plus 5. And just like before, I have to subtract it. But they're the same expression, so when I subtract, I get 0. So what this tells us, just like before, is that x cubed minus 5x squared minus 9x plus 10 is equal to x squared minus 7x plus 5 times x plus 2. And we just like before, it was this times this plus a remainder. We have this times this, which came from, gotta get my picture out of the way. This times this equals that with no remainder, because the remainder was 0. So we're going to do one more example for computing this, but let's just write down the division algorithm that is driving everything that's going on here. So first we'll write it down for real numbers. So for numbers, the division algorithm goes like this. Given any integers p and d, where d is less than or equal to p, there exist two integers q and r such that p equals q times d plus r. So this looks complicated, but it's exactly what we said here. So this is the p. So another way to write this is if you do p divided by d, it's going to equal q plus r, essentially. So this is our p. This is what we're dividing by, the 32. So I can write it as 32 times something plus a remainder. So this is the 32 times something plus a remainder. In other words, if I take p and divide by d, I get some quotient, this thing, plus a remainder. Okay? Or this actually isn't plus a remainder, this is with a remainder. Okay, so we have a similar thing for polynomials. Oh, and the other important thing is that r is less than d. That was like what we said before. If the remainder was bigger than 31 or bigger than 32, we could have fit another 32 into that. So for polynomials, what the division algorithm says is given two polynomials, p of x and d of x, where instead of one being smaller than the other, we have that the degree of d of x is smaller than the degree of p of x. Then there exist polynomials q of x and r of x such that p of x equals q of x times d of x plus r of x. And again, instead of r actually being smaller, all we need is that the degree of r is smaller than degree of d. And that's like the polynomial example that we just computed. So here's our p of x. We divide by d of x. We get some quotient, and here the remainder was 0. So this says p of x equals d of x times q of x. Okay, so I'm going to stop this video here, but I'm going to do another example and we'll come back to the division algorithm in the next video, and we're going to talk about how this can actually be used to help us find zeros.